All right, the recording has started. So good morning, everybody. Welcome back to Math 115. I hope everybody had a restful weekend. Let me check in with the class. How are things going? Is homework going okay? Is the class going okay? Is life going okay? All is well. Class is going great. Okay, that's good. Anyone else want to weigh in? Party too hard on the weekend. Nice. Congratulations on your chem exam. Okay. Well, good to hear that things are going pretty well. Don't forget, if you ever have any suggestions for the class in terms of ways in which we could improve the class, then you can always fill out the anonymous survey on the Blackboard. So it's a Google form. I won't see your email. I won't see who you are. You can leave me a note and say, you did this section way too fast, or my God, the pace is so slow, or you blazed through this one topic when you should have spent more time on it, etc. Things like this. If you have suggestions about the homework or exams and stuff like that, I'm also open to those. So that's an option for you guys to provide feedback to me if you don't want to provide it during class or emailing me or whatever. Okay, so a couple of reminders before we start. First of all, exam 3 is going to be on April 8th. And I'd like everyone who's in the class right now and everyone who is watching the YouTube video on a delay to please mark your calendar or somehow make sure that you know that when it's April 8th, it'll be time to do the exam, okay? And it'll be due at 9 p.m. on April 8th. Okay, this is the usual time which our exams are due is 9 p.m. on April 8th. Okay, so please, 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 please mark your calendar because there have been students who've gotten burned by, I don't know if they're maybe not watching the lectures or they're not paying attention to the start of the lecture when I'm always harping on when the exam is. But this is when the exam is, and I know with these online classes it can be hard to remember, but that is when it's going to be. So please mark it, set a reminder in your phone. I don't know, write it on the wall in blood. Just make sure that you know that this is when the exam is going to be. Okay. Also, we have a homework due every Friday at 11:59 p.m. So, I'm not going to necessarily remind you of every single homework that we're going to have. It's just that is when the homeworks are due every Friday at 11:59 p.m. So that should be easy to remember. If you want to set a weekly reminder in your phone, that would also work. Or if you have a calendar or a planner, just fill it in for the whole rest of the semester. You're probably going to have a homework due on every single Friday, with the occasional exception, but that's when the homework is due. Also, exit slips due 1 week after every lecture. Okay, and exit slips are worth 7% of your grade. So please complete them. 7% of grade. And homework is worth some amount, which I don't remember what it is, 20%. Homework is worth 20% of your grade. Okay, so make sure you're doing those homework and make sure you do those exit slips. We do have in the syllabus an allowance for you can miss one homework assignment without incurring a penalty, and you can miss 2 exit slips without incurring a penalty. So if you're within that range, then you should be okay. Or if you just do badly on a homework assignment, you know, the lowest one will be dropped. So that's kind of your extra credit, as it were. All right. Any questions about, do I drop 1 exit slip? Yeah, I dropped 2 exit slips. So yeah, 2 exit slips will be dropped. Okay, any other questions about administrative aspects of the course? Okay, if not, then we'll start. Okay, so last week we continued our discussion about trigonometry, and we are going to continue with trigonometry for at least another, basically at least until exam 3. And then, you know what, let me actually check what comes after that. I have the book here in front of me. After exam 3, we're going to talk about more trigonometry. Okay, so the whole rest of the class is going to be trigonometry. And basically, we're taking the following path. 2 weeks ago, we just learned what are the definition of trigonometric functions. Last week, we learned, okay, what are some of the properties of these functions? What are some of the identities of these functions? Very basic identities. And what are the graphs of these functions? Okay, and we didn't quite finish the discussion on graphs, which we're going to finish up today. But this week, we're going to talk about how we use inverse trigonometric functions, okay? So can we actually go back and get the angle back from the value? And we're going to talk about analytic trigonometry, which let me say more about that later this week. And then after that, we're going to talk more about analytic trig, and then we'll have the exam, and then the very last chapter will be applications of trigonometry. So pretty much all unit circle and trig from here on out. So if you're not super comfortable with the unit circle and stuff, I definitely recommend that you go back and watch those early lectures when we established what is the unit circle, what is sine and cosine and tangent and cotangent and secant and cosecant, and have an understanding of how to, you know, get around, as it were. Okay, so inverse trig, we might say for next time, depending on how far I get through today, because I need to go back and sort of review what I was talking about last time and finish up that discussion. So our discussion on Thursday was kind of revolving around the graphs of trigonometric functions. Okay, and the way that we graph the trigonometric function is we essentially let the horizontal axis here, and this graph is messy, this one's better. We let this horizontal axis here, we let points which are on the horizontal axis describe the angle measurement which we are going to put in the unit circle. Okay, so when the x value or the horizontal value of our graph is at pi, then we're going to make a unit circle and we're going to draw the angle pi on the unit circle. And then the height of the graph at that point, depending on whether we're talking about cosine or sine or tangent, is going to depend somehow on the values of these points x comma y. So if it's sine, then we take the y value of that point, which corresponds to the angle pi, and we would plot it. or in this case, this blue graph is cosine of x. So we take the x value, which for this point would be -1, and we take that x value -1, which is the cosine of pi, and we graph that to be the height of our function at that point. Okay, so there is a correspondence which goes between these two things, okay, which is really kind of nicely encapsulated by this animated thing I put up here. Okay, so as the hand of our clock basically goes around clockwise in this circle, okay, we can think about the x-axis as kind of moving in this direction at the time being. Okay, so if we really wanted to understand what's going on here, we'd have to kind of move the whole thing to the right as this was graphing, but we can't do that. So just imagine, like, you know, pi is like stationary and it's, you know, right here, and as this graph moves to the left, it's also moving to the left. Okay, so this is kind of the correspondence we have between what's happening with, you know, your angle here, theta. Okay, this angle theta is then going to produce a point which is on the unit circle, and then the height of our graph is just the height of that point on the unit circle, or maybe it's the width of the point on that unit circle if it's cosine, or maybe it's something like a ratio between those two values if we have a tangent or a cotangent or something like that. Okay, so we learned how to graph sine and cosine, and really this was kind of the picture that we had for understanding that. Okay, so what we do, let me clean it up. What we do is we just take a given angle. Okay, so take the angle pi/6. We put it on the unit circle, and then we look at this point which is on the edge, which is the point something something, x comma y maybe. I don't remember exactly what it is off the top of my head. Oh, it looks like it's probably 1/2, and so this is a 30-degree angle. So this is 1. So this is a 30, 60, 90 triangle, and that's 1. So this x should be 1. No, x should be square root 3/2, and y should be 1/2. Okay, I used the Pythagorean theorem to figure that out. And the fact that this is a 30, 60, 90 triangle, I memorized those side lengths. Okay, so then if we're making a sine graph, then the height of the graph for that given x value is going to be the y value of the point on the unit circle, which we get if we inscribe the angle pi/6 inside the unit circle. Okay, and if instead we were using cosine, if we were doing cosine of x, then what we would take is instead we would take the x value of the point on the unit circle, which corresponds to pi/6, and it'd be somewhere a little bit higher because it's a bigger number. In fact, cosine looks kind of like this. And down at pi, it takes a negative minimum, and then it comes up again. And then we finish out again at 1 here. So here's kind of what cosine looks like. All right. So it's just depending on whether we are taking either the x value or the y value of this point on the unit circle, which corresponds to that thing. Okay, so this is what we talked about last time. And at the very end, we kind of talked about, okay, well, these types of graphs all fall into a class of functions, okay, and graphs which we call periodic, okay? And we have special words for describing the attributes of a periodic graph, okay? And there are two important words that we use. The first one is the amplitude, okay, which is going to be the wave height, Okay, how tall is this wave from regular kind of, if you imagine the x-axis as being sea level, then it's the height of the wave above sea level when it's at its maximum height. Okay, so we count from the x-axis up to the top of the wave. Okay, so one thing to not get confused about is don't go thinking that the amplitude is the distance between the lowest point and the highest point. That'll give you double of what you want. Okay, and then the period we defined in the following way. It's basically the amount of time that it takes for the wave to repeat itself. Okay, and the easiest way to measure that is to go from crest to crest, okay, because there's only one crest in each repetition of the wave. So I call this red box basically one repetition of the wave. It goes up and then it goes down. And then once I get back to that pink point, I'm starting over. Okay, so the way we count how long this red box is a little bit more clever. We just move it over a little bit and measure, well, okay, if I go from crest to crest, I know that's definitely going to be one repetition. And so that's how I measure the period of this wave. Okay, the reason I don't leave the box over here and say, well, how far is it from, you know, the origin to this point bx equals 2 pi? Well, the reason is sometimes students can get confused and say, okay, well, maybe the period is the distance between, you know, between these two zeros. And that gets people confused and they wind up getting half of the period. Okay, so that's why we measure from crest to crest of our waves. Okay, so those are the two words we use to describe periodic graphs. Okay, so if we have a sine graph here, which is transformed a little bit, okay, it's vertically stretched by a factor of a, and it's horizontally stretched or shrunk depending on the value of b. Okay, and so this point here, where we reach the end of our cycle, is going to be the point where the inside of this function is equal to 2 pi. Once the inside of that function is equal to 2 pi, well, we know that b times the x value should be equal to 2 pi. So we know the x value, which is at this point where we finish our graph, is going to be the x value 2 pi divided by b. So if b is something like 6, then this would be like pi over 3. Okay, so it's going to scrunch our graph to the left, or maybe it'll kind of extend it to the right, like a slinky. I wonder if I can find a GIF for a slinky. Let's see. I was looking for a longitudinal slinky. All right, sorry people, there's no good slinky GIFs. All right, so that's about amplitude and period. And what we were about to talk about is, okay, how do we understand what happens to the graph of a periodic function like sine or cosine when we have a horizontal shift? Okay, and there's a very fancy term which we use to describe horizontal shifts for periodic functions. Okay, and we call it a phase shift. Okay, phase shift. So set your phaser to stun and let's learn about this stuff. So basically, we see something like this, where we have a sine function or a cosine function or whatever, okay, some periodic function, and we've got a translation in here. We're going to deal with it the exact same way that we always deal with horizontal shifts. Okay, all I'm going to do is I'm going to take this graph here and, oops, Why don't I even change the color? All we're going to do is, depending on whether this is a plus or a minus, okay, we're going to move our graph to the left or to the right. Okay, so let me ask the class, what do we think we should do with this graph first? Since we've got a sine of x minus pi over 2, should we move our graph to the left or to the right? Okay, does everyone agree we should move it to the right, like Om Kumar and Abdul Rahman say? Heidi weighs in as well, to the right. Okay, I think we're correct. All right. We have to remember, when we have a minus sign on the inside, when it's on the inside of the parentheses, okay, it's going to move us left and right. And we got to remember it's sort of the reverse of what we think it's going to be. Okay, so we got to move it to the right. Okay, so I'm just going to take the whole graph and I'm just going to up and move it pi over 2 units to the right. Okay, so I'm going to take it, I'm going to move it to the right. Just going to take it and move the whole thing over to the right. Okay, and if I were to, draw a little bit more, what would it look like? I mean, something like this. Oops, got a little bit tall there at the end. Something like that. Okay, and then I gave this little dotted line to show, okay, it's carrying on in that direction. I'm just doing that forever and ever. Okay, so here's a phase shift. We just phase shifted this graph of sine of x pi over 2 units to the right. Okay. By the way, let me show you something cool. Well, I don't know. I think it's cool. Maybe you guys won't think it's that cool, but I think it's great. Let's try also on the same graph. Let's also graph. What about y equals sine of x? Is that going to work? Plus 3 pi over 2. Okay, what happens if we graph this? Well, we can take our whole thing here and maybe move it over a little bit so that we have a bit more room on the left, because we're going to phase shift now to the left. Okay, so let me put on, here's like pi over 2, negative pi over 2, and let's see here. I think that should be like negative pi, and then all the way on the left is like negative 3 pi over 2. Okay, maybe this isn't going to work out quite as well as I was hoping, just based on the graphs. Okay, but if we move this whole thing over, this blue graph here, we just copy and paste it again. And we move this whole thing over. This time I'm going to move to the left, pi over 2, and then I'm going to move pi, and then all the way to 3 pi over 2. And what I'm going to wind up creating, okay, is something which looks just like this orange graph here. Okay, if I move it all the way over, then what is it going to look like? It's going to look like this. Okay, forget about that end part. Make it look better. All right. So it turns out, okay, if we make a movement of our graph, pi over 2 units in one direction versus 3 pi over 2 units in the other direction, we wind up with the same picture, which is kind of intriguing. Well, it makes sense if you think about it, because if we have a function which is 2 pi periodic, okay, if we are then to take this graph, right, and move it a certain distance in either direction, at some point it's going to overlap with the original function. So if I copy this and paste it, well, if I start with it overlapping, if I move it far enough, it's going to actually overlap again with what it was originally. Okay, it's going to overlap. So if I move it far enough, then it looks just exactly the same as it was before, which is kind of curious. And if we move it in either direction, if we move it just the right amount, then it'll overlap perfectly. Okay. And this is all coming from the fact that this function is periodic. We know that sine of theta plus 2 pi is equal to sine of theta, right? So in particular, the functions sine of theta plus 2 pi and sine of theta are equal if we graph them, which means if we were to graph them, their graphs would overlap. Okay, so that's just kind of a cool thing we can do with phase shifts. Okay, so basically phase shift is just a horizontal shift. That's all I was trying to say here. Okay, just a horizontal shift. All right, so now we have pretty much everything we need to be able to graph functions of all sorts of types using the trigonometric functions. And the way I'm going to view this one and pretty much every trigonometric function from here on is going to be as a transformation of the original function. Okay, so it's worth memorizing what do the graphs of sine and cosine look like so that you can then manipulate them and graph things like 3 cosine pi over 2 minus x over 2 or whatever as just a transformation of those graphs. Okay, so the original cosine graph looks like the following. It looks like it starts at 1, and then it comes down here through pi over 2, and then it reaches a minimum at pi, and then it comes up back through 3 pi over 2, and then it reaches a maximum then at pi over 2. Okay, and here's what original cosine of x looks like. So what I'm going to do is the following. I'm going to use my translations and shifts and whatnot in the order that we have them. So let's write down what we should do. First of all, it looks like we do have a horizontal shift. We've got a plus pi over 2 on the inside, so this is going to move us left pi over 2. We have a stretch and a compression in both directions. We have a horizontal stretch by 2, vertical stretch by 3. And then for reflections, well, we do have a negative sign on that x over 2 on the inside, so that's going to produce a reflection about the y-axis. And we don't have any vertical shifts. Okay, so this was an order of operations which we learned when we first learned how to do transformations of functions, and now we're going to just apply that theory to something new. Okay, so we're just going to take this new graph, which we're not super comfortable with yet, but we know that it should obey the same basic principles when we transform it. Okay, so let's do it. So first, let's take this. Let me see if did I draw this in 1? I hope I did. No, I didn't. Not at all. Let me see if I can draw it in 1 so that I can actually move this thing. Okay, so first things first, what should we do? Well, we should move it left pi over 2. So I just take this whole thing and I up and move it left pi over 2 units. And then I should do a horizontal stretch by 2 and a vertical stretch by 3, which means that everything should just get moved up by 3 units and out by 2 units. So let me go up by 3 first. It'll look something more like this. Okay, that's my vertical stretch. Okay, and now I want to do a horizontal stretch by 2 units, which means that the point which goes through the x-axis should move from where it is to double of where it is. So it should move from there to here. So my final graph is going to look something like, well, it still goes through the x-axis at 0, since 2 times 0 is still 0. So it goes through the x-axis here. It reaches a minimum at pi. And then it comes up and it goes through the x-axis at 2 pi, and then it won't reach a maximum again for another pi units. Okay, so finally, our graph looks something like this. Okay, and we can erase whatever we put in between. Okay? And we can always check and make sure that we've done this right. Let's see. We know that cosine of x has a 0. No, why don't we say cosine of x equals -1? Well, when is cosine of x equal to -1? It's going to be equal to -1 on this point, -1 comma 0. Since cosine refers to the x-coordinate, we want the x-coordinate to be -1. So we know that happens when the angle here is pi. So we should double check and see, does our graph reach a minimum when this inside function is equal to pi? So we can do that by taking a look. Well, this graph that we drew reaches a minimum at pi. So the question is, if I plug in pi into this function, yeah, if I plug in pi to this function, I should get pi inside. Oh, there's one thing I forgot to do. Shoot. I forgot to reflect about the x-axis, about the y-axis. So finally, I would take this whole graph which we drew. Sorry guys, I forgot to do the reflection. 1 second, Sam, I'll address that in a second. So if we reflect, what does that look like? Looks like this. And then we should probably move this whole thing over. If we reflect, it would look like that. And then come down and up and so on and so forth. And it's going to reach its minimum actually at -pi. That makes more sense. It looks something like this. And then, so on and so forth. So if we plug in -pi into our inside function here, if we plug x equals -pi, we should get pi on the inside because cosine reaches a minimum at that point. Well, if I do pi over 2 minus -pi over 2, I get pi over 2 plus pi over 2, which is equal to pi. So the point which would be reaching a minimum on the cosine of x graph basically got moved over here, and then this height which we're reaching is positive 3 and -3 due to our vertical stretch. Okay? So what we need to remember when we're graphing functions like trigonometric functions with phase shifts and stretches and reflections and all of that stuff is just remember the principles which we learned from our original chapter on transformations, okay, which I think was like 1.5 or 1.7 if you want to go back and check out that video. We just need to remember, okay, what's the order in which we apply these transformations? What does the graph of my parent function look like? And then let's just apply those transformations in order. Okay, and this will give us the graph. Okay, so let's see maybe a demo real quick using Desmos. Let's see what some of these different functions can look like. So let's see here. So first of all, let me block that one out and that one. So here's what the graph of sine of x looks like. Okay, so if we take a look at this function number 2 here, where we take this multiplier by 2, okay, well, what is it going to look like? It should vertically stretch our graph, so it looks something more like this black graph. Okay, as usual. And if we put the 2 on the inside, then, well, we know that should give us a horizontal shrink by basically a half. So let's see what it looks like. Again, it looks the same. So what does it look like? Well, the point at which, and I don't have like a highlighter or a pointer here, but okay, if you look at the point on the purple graph where we first cross through the x-axis, it's at pi, right? Because sine of pi is 0. Well, that point gets moved over towards pi over 2. Okay, that's what happens, because then 2 times pi over 2 would be pi, would be 0 on our original function. Okay, and then, you know, we can put stuff on the inside too, like plus 3. Well, what is that? How does that affect things? It just, or plus 1 maybe. Well, it just moves everything that we just had to the left 1 unit. Okay, so it did go through 0, 0. Now it goes through the point -1, 0. Okay. So this is basically just how we're doing this. It's just a transformation of these functions. Okay, let me address what Sam asked. So the question was, is sine of x minus pi over 2 the same as sine of x plus 3 pi over 2? Absolutely. That's almost what we had here. Actually, this is what we had here. Yes, these two functions are actually the same. Okay. For the same reason that if I said, let's look at a point on the unit circle which corresponds to an angle versus a point on the unit circle that corresponds to that angle plus 2 pi. Well, if we look at this point which corresponds to theta, and we look at the point which corresponds instead to theta plus 2 pi, well, they're the same angle. Well, they're coterminal anyway, so they point to the same point on the unit circle, which is why if we take sine of theta, it's going to output the y-coordinate of this point. And if we take sine of theta plus 2 pi, well, it's going to output the exact same value because that angle points in the same direction as our original one. So yes, those two are the same. And really, by the same, what I mean is if we plug the same x value into both functions, we're going to get the same y value. I mean, they're sort of functionally the same, although technically we're plugging in a different angle, but, well, when we plug in an angle which is coterminal, sine outputs the same thing. So the sine function is sort of covering up the fact that we've even done a phase shift at all. Okay. Yeah, so that's what's going on there. Okay, so, you know, look, if you don't immediately understand everything that we did in this example about graphing this really complicated transformed cosine function, don't panic, okay? What you might need is some practice graphing cosine and sine using the usual method, and then some practice transforming them. Maybe start with just a vertical shift, start with just a horizontal shift, and so on and so forth, and build to complexity. But this was an example that I just wanted to give so that I can show you guys what it looks like if we have everything all at once. And we got to just remember that we should do these shifts and transformations in this special order, which I've written down here. And if we just do those in their order and identify them one by one, then we're going to get where we need to be. Okay, any questions about this example? Okay, if no questions, then I'm going to move on. Oh, actually, we're going to take a GIF break because I think that was a hard one. Oh, yeah, and I even put in some periodic motion in here. So here we've got this little dog here. And if you were to graph the height of the swing, right, at a given time t, okay, so here's 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds, and so on. Well, you'd notice that the height of the dog on this swing is going to actually follow more or less a trigonometric function. So we're going to get this kind of periodic motion. So don't forget, this periodicity here is really just talking about repetitious movement. Okay, I hope we feel better. All right. So probably the last thing we'll talk about today will be, okay, we know how to graph sine and cosine, and we know that tangent and all those other trigonometric functions are just combinations of sine and cosine. So how should we graph those functions? Okay, and it comes down to the following. Basically, we just take the graphs of the sine and cosine function, and if we want to know, well, for a given x value, what should be the height of the tangent function? We just check what is the height of the sine function and what is the height of the cosine function, and we divide them, since tan of x is equal to sine of x divided by cosine of x. We're just going to take this height, which we know to be sine of x, and we're going to divide it by this height, which we know to be cosine of x. So for every single point, we're going to do that. Okay? And you might notice that there's going to be one really big, sticky problem with graphing tangent of x. Can anyone tell me in the chat what that sticky problem is going to be using this method to graph tangent? I'll give you a hint. Something bad is going to happen when we try to use this process at the x value, which is highlighted in yellow here. Anyone see the problem? not two solutions. Let's look at the definition of tangent. We want to take the height of the sine function, which for this highlighted part, the height of the sine function is 1. And we want to take that number and divide it by, we want to divide it by the height of cosine, which at this point is 0. So the problem with this method is at every point where cosine passes through the x-axis, the denominator of this function is going to be 0. Yeah. And now we see. Okay. So let's see how it looks. Well, what's happening? Wait a second. Something's wrong here. Okay, yeah, no, we're fine. So let me just extend these functions a little bit in the other direction as well. In this yellow, and go down, and sine is going to go like down like this. It's going to go down more like this. And here's -1. And this is 1. And this just goes through the x-axis at that point, which is the point -pi/2. And here is pi/2. Okay, so what's happening with the graph? Well, let's start over here at -pi/2. As I get very close to -pi/2, I have that we have sine of x is a negative number, something close to -1, and I have cosine of x going to 0, but still positive. So if I want to consider, well, what is the limit as x goes to -pi/2 from the right of sine over cosine, well, as we get very close, sine of x is very close to something like 1, and then the denominator will be something which is very small and positive. If we take some positive number and divide by something very, very small and positive, sine of x should be negative. We take a negative number and divide it by something very, very small and positive, then we're going to get that this is going to -infinity at this point. So when we want to graph tangent of x, we're going to notice that at the point -pi/2, this is actually going to be a vertical asymptote for our function. And we even know what the behavior of the function should be. We know the behavior of the function should be that we're going down to -infinity at that point. Okay? And then what happens as we move to the right? Well, I'm going to march from -pi/2 to the right until we hit 0. And let's see what's happening. Well, cosine is sort of calming down. Our denominator is going from 0 to 1. And our numerator is going from -1 to 0. So once we hit x equals 0, okay, then we're going to have the following. Tangent of 0, we know that should be equal to sine of 0 over cosine of 0. And in this case, we know sine of 0 is just 0, and cosine of 0 is just 1. So we get that tangent of 0 should be 0. So our graph is going to look kind of nice and smooth coming up here up until we hit 0, 0. And then on the opposite side, we're going to find that we have the opposite behavior. Okay, and I'm not going to go through it, but I'm going to show you really quickly. It should look something like this. We're going to have asymptotic behavior on the other side as well. Okay, so this is how we graph the tangent function, and I'll finish up this discussion about this next time because I'm out of time. So thanks, everybody. I have office hours starting now and going until 10:30, so if you're confused about any of this stuff, please stay after and we'll do more examples. Otherwise, everybody have a great day, and I'll see you tomorrow.
Hello, Professor.
Hi, I'm Kumar. Did you have a question or want to see an extra example?
Yes. So the thing is that I want to learn the anatomy of a periodic function again.
Sure. No problem. We can go back through that. Okay. So let me give us an extra page here, and we'll start a little bit further back. Okay, so let's consider the function y equals sine of x. Okay, what does this function look like? Well, let's remind ourselves. We have x-axis here, and we have the y-axis here. Okay, and what we do to get the height of the sine function is, for each x value, we're going to make an angle in the unit circle where the measure of the angle is equal to that x value in radians. So what we do is we draw a unit circle. Okay, and first let's consider, well, what is happening when the x value is 0? Well, when the x value is 0, what we should do is draw a unit circle first. Okay, when the x value is 0, we should draw an angle which starts facing to the right and ends facing to the right. And that point on the unit circle is this point 1, 0. And the height of the function sine, y equals sine of x, well, sine we know corresponds to the y value of the point on the unit circle for that angle. So in our case, it starts at 0, 0, because when we plug in sine of 0, we get 0. Okay, and then the height of all the other points is going to come from doing other angles. So when pi over 2 is our point, okay, then the height of our sine function is going to be determined by the angle which we form in here using pi over 2 as our angle. Okay, so here is pi over 2. And that shoots us up straight up at that point 0, 1. So at this point, the y value of the point on the unit circle is 1. So we know that the height of our function at this point should be 1. Okay, and so on and so forth. And we're going to use this process to draw the graph of our sine function. It should look something like this. Oh, crap. Something like this. Okay, so are we good so far on how to graph a function like sine?
Yes.
Okay, and does cosine of x give you any trouble?
No, it's okay with me.
Okay, so all this is good. So really, when I talked about this anatomy stuff, I'm just talking about words we use to describe periodic graphs. Okay, so the words we have are the following. If we have a graph like this, which repeats over and over and over again, we want to consider properties of one single repetition of the graph. Okay, so if we were to take what's in this box and copy and paste it on the right and the left 1,000,000 times, we would have the entire graph. But I know that all of the rest of the graph is sort of determined by what's happening in this yellow box. Does that make sense?
Again, what was that?
Okay, so I'm hoping to, hang on, let me graph this in a way that I can copy it. Okay, so if I wanted to graph this function, what's going to happen next? Well, what's going to happen next is the graph is going to look exactly like this again to the right. And then again to the left. Okay?
Yes.
So my point is, if I know what's happening to the graph in this region, then I know what the graph looks like everywhere else.
Yes. Yes.
So I want to describe what does this part of the graph look like so that I know what the whole rest of the graph looks like.
Okay.
There are two things that I want to say about this part of the graph. The first question is, how long is it? This is what we call the period. It's basically how long for one repetition. Okay? How long does it take for the point of my graph to end up basically at the same height and pointing in the same direction as it was before? Okay?
Okay.
So that is what the period is. Okay? Now the amplitude is the second question. Well, we know how long it is. Second question, how tall is it?
Okay.
And we call this the amplitude. Okay? So here's what I drew. I drew a function which had been transformed. Okay, so our function was the function y equals a, so some number a, times sine of some number b times x. So this is the function which I just drew, except it's been transformed in the following way. We have a vertical stretch of a units, and we have a horizontal compression of b units, or stretch, depending on if a and b are smaller or larger than 1, then we might have a stretch or a shrink. Okay? And so now what I want to do is look at this graph and say, well, if I were to draw on my box again, it'd be, let me use green. This green box is like one repetition, right? If I know what's going on in this green box, I know what's going on everywhere else, right? But I can also think of this box as being anywhere, right? I could think of it also being here, because I know that if I just take what's inside this green box now and copy it over and over again, it's still going to be what our entire graph is, right?
Yes.
So if I want to find the period, the reason that I drew the period from the crest to the crest instead of like this, okay, is because sometimes it can be tricky to see on the graph, well, how long exactly is it from basically start to finish of a repetition? But it's really easy to tell if you go from crest to crest, because you know for sure that if you're at the crest, that only happens once in every repetition. Does that make sense?
Yeah, but we have two crests, right?
Yes. Okay. So how should I say that then? My point is, if we
I think I
consider,
got it. I think I got it.
yeah, if we consider like what's happening here, the issue with using this box is we go through 0 3 times in the box.
Hmm.
you know? So some students can get confused and think that maybe the box should be right here,
Yes.
and that will give you the wrong length for the period. So instead we say, let's just make it go from crest to crest, and then we know for sure that'll definitely be the period.
Yes. Yes.
So that's just, one way of defining it. If you want to take your box to be here, that's fine. I just caution you to make sure that you don't make the mistake of saying that the period is, this length here. Because
Hmm.
if we just repeat that over and over again, what we'd get is a graph which looks like this,
Yes.
which is not what we want.
Hmm.
Okay, so that is what the period is. It's just a measure of the length from crest to crest. And, we know that sine is 2 pi periodic, right?
Yes.
So we know that sine of theta equals sine of theta plus 2 pi. So if we want to know, well, what is the period, basically, of sine of bx? Well, we want to say, well, for what value of b do we get sine of bx is equal to sine of b times x plus p, which we call p the length of the period. Okay, this is what we want to know. What is p such that this is true? Well, if we want to know the period of sine of bx, well, we just solve this equation in the following way. Well, we know that bx should be equal to b times x plus p plus 2 pi, based on our previous understanding that sine is 2 pi periodic. We know that if we take sine of if we take sine of b of x plus p, okay, if we were just to basically add in 2 pi right here, then we know it wouldn't change the value of sine because
Yes.
of this. So if we just solve this for p, we're going to get the following. Well, if we distribute the bx, we'd get bx equals bx plus bp plus 2 pi. And we'd cancel the bx's. And then we get bp equals negative 2 pi. So then p is equal to negative 2 pi over b. But remember, period is a length. So if we have a negative value, it should be a positive value, really. So this is just the period is 2 pi over b long.
Okay.
And this is how we get that this point right here should be the point x equals 2 pi over b, because that is exactly how long this distance is. Okay, so that's
Yeah.
one way that you can find the period. Okay, you can also just say, well, if you want to know what is the period of sine of bx, you can just view it in the following way. If I start with sine theta has a period of 2 pi. Well, if I compress that graph by a factor of b, then the period will be compressed by a factor of b. So that's maybe the cleaner way of thinking about it. Or maybe the more intuitive geometric way of thinking about it, whereas this is what I wrote down is more analytic.
Yes.
Okay, so this is basically what's happening. So, and you can see it in Desmos too, right? We did an example of this one. Here, let me show you. We'll do sine of 2x. So you can see that the length it takes for sine of 2x to make a complete crest to crest is half of the length that it takes for sine of x to make a complete crest to crest.
Yes.
So its period will be half of the period of sine. Since the period of sine of x is 2 pi, the period of sine of 2x will be just pi.
Yes.
Okay. And then what would change the amplitude? Well, the amplitude is the height of the wave. I know that the height of the wave is always 1 for sine. But if I were to multiply by 3 out front, then that will give me a vertical stretch. And now the amplitude of this function is 3.
Yes. Yes.
Okay. So this is all I was trying to say about the anatomy of the periodic graph, was just to explain what does the word period refer to and what does the word amplitude refer to, and give you a tiny bit of information about how to find it in this sort of simple case.
Okay. Okay, then. Thank you.
Yeah, no problem. Let me put on my headphones. Do you have more questions about this stuff?
No. I understood it.
Okay, cool.
Yeah. Thank you. Have a good one.
Yep, you too. Sam, did you have any questions?
Yeah, when I was doing the homework and I was doing some arithmetic, I think I messed a couple of things up with some square roots. So I was gonna ask if you could go over the problem for me.
Yeah, sure. Do you have the problem in front of you, or you want me to check it on?
I had did 1 divided by the square root of 3 over 2.
Okay, hang on. 1 divided by the square root of 3 over 2, like this?
Yeah, and I think the answer that they gave was it was supposed to come out to 2 square root of 3 over 3.
Those are equal.
Yeah, I just couldn't, like, I don't know, I think I messed some arithmetic up or something, because when I was evaluating it, I don't know, it just gave me a really hard time for some reason.
Okay, yeah, no problem. I think I know where the problem came in. So first of all, if we take a number like 1 and we divide it by a fraction, this is the same as doing 1 times the reciprocal of that fraction, right? Is this stuff clear?
Yeah.
Okay, and you did that?
Yeah.
And I'm guessing you got to 2 over square root 3 and you were like, WTF, these are not the same.
Yes. Exactly.
Okay. And the trick here is there was something that we learned, which is that when we write a fraction like this, it's sort of improper to have a square root in the denominator. Do you remember that?
Yeah.
And do you remember what we did to solve that?
I do not.
Okay, so this step is called rationalizing the denominator. And the goal here is to rewrite this fraction in a way that's we're saying the same thing, but it looks better in the sense that the denominator is not irrational. Okay, so no square roots in the denominator is basically what we're after. So we think of to ourselves, well, how could I possibly undo a square root? Well, if I squared it, then that would undo it, right? So what if I were to say, multiply this times the square root of 3 divided by the square root of 3? Then I just take some number and I multiply by 1. So I get the same number, right?
Right.
So you agree that if I multiply by the square root of 3 over 3, square root of 3, I haven't changed anything.
Right.
So if I do this, well, how do I multiply fractions? Straight across. So 2 times the square root of 3 is what I get here. And then if I do the denominator, I get square root of 3 squared.
Okay.
And that's equal to 2 times the square root of 3 over 3.
Oh. Okay. I think when I got to 2 over the square root of 3, I like second guessed myself and went back and thought about it too hard.
Mm-hmm.
Okay. They gave another one that was similar. It was negative 1/2 divided by the square root of 3 over 2.
Sure, we can do this one again. So if we do negative 1/2 divided by the square root of 3 over 2, it's the same as doing negative 1/2 times 2 over the square root of 3, right?
Yeah.
Okay, and then I cancel the 2's. And I get, what do I get?
Negative 1 over the square root of 3.
Okay, and how can I rationalize this?
Times it by the square root of 3 over the square root of 3.
Good. And what do I get on top?
Negative square root of 3.
And on the bottom? Yeah.
Okay.
Yep. That's how we rationalize those.
Okay. Yeah,
Okay.
I think I've had a lot of problems with I think radicals and rationalizing stuff has always given me problems. I'm not really sure why, but
All right. Well, do you have a little bit more time to go over a bit more?
sure.
Okay, then I'll do that. So let's see here, add a page. Okay, there's one thing that I want you to be aware of, which is that if I have something like 2 over the square root of 3, and I want to rationalize this, I want you to be aware that this is not the same. I can't just take this and square the whole thing. If I square the whole thing, I'd get like 4 over 3, right?
Yeah.
But here's what I want you to be aware of. If I take a fraction like 1/2 and I square it, okay, it's not still equal to the same fraction I had before. This is the problem with this method. Okay, so if I take 1/2 and I square it, that's 1/2 times 1/2 equals 1/4. In other words, if I square a fraction, I haven't multiplied by 1, I multiplied by whatever that fraction was. Okay, so I have changed the expression. So I just want to point this out and say this is not how we rationalize denominators. If we want to rationalize a denominator like 1 over the square root of 2, we have to multiply by square root of 2 over square root of 2 so that the thing that we're multiplying by is equal to 1.
Okay.
Because if I take a number a and I multiply it by 1, then I get back just a. I haven't changed the number.
Okay.
So that's the one thing to avoid. And then there's another thing which you should be aware of, which is, well, how do I rationalize something like 1 over 1 plus the square root of 3? Okay, and the trick here is really pretty clever. We want to multiply by something again. We want to multiply by 1 in a clever way. Any particular things come immediately to mind? It's okay if not. This is kind of a harder one.
Could you put 1 plus the square root of 3 over itself?
Let's try that. That's a good first guess. If we do this, we'll get 1 plus the square root of 3 on top, right?
Right.
And on the bottom, we'd get 1 plus the square root of 3 squared. And if we were to square that out, well, it'd be a FOIL, right? And if we were to FOIL that bottom part out, we would get 1 plus square root 3 plus square root 3 plus 3. So in the end, we get 1 plus square root 3 on top, and on the bottom, we get 1 plus 2 square root 3 plus 3. And so there's an issue here, which is we still have a square root in the denominator.
Okay.
So my question to you is there a way that we could modify this denominator here so that when we added up these square root 3's, they would cancel out? so that one of them would be a plus and one of them would be a minus?
You could check. Well, I guess you'd have to figure out a way to change the sign of one.
Exactly. Let's try that. So what if instead of this we did the following? I know my original function is 1 over 1 plus the square root of 3. I can't change my original function, but I can change the thing that I multiplied by. And instead of multiplying by 1 plus the square root of 3, I'm going to multiply by, like you say, 1 minus the square root of 3. Divided by 1 minus the square root of 3. I just need to make sure this top and bottom are the same so that I'm multiplying by 1.
Okay.
Okay, let's see how this one works out. Well, the top, we get 1 minus the square root of 3. And on the bottom, we would FOIL these guys. So what do we get? Well, 1 times 1 is 1.
Hi.
1 times negative square root of 3 is negative square root of 3. And then 1 times positive square root of 3 is plus square root of 3. And then positive square root of 3 times negative square root of 3 is negative 3. Or if you want, it's negative square root of 3 squared. So then we see what happens with these two middle terms. They cancel. And then the bottom here is now just, well, we have 1 minus square root of 3 on top, and the bottom is just 1 minus 3. So we get 1 minus the square root of 3 divided by negative 2.
Okay.
Okay, so that's how we cancel when our denominator has a sum involving a square root here. Okay, if it's a sum, then what we have to do is multiply by what is called the conjugate. All right. So these two terms, 1 plus the square root of 3 and 1 minus the square root of 3, we call those conjugates. Basically, we get them by keeping the first number the same, and we change the number which is attached to the square root.
Okay, that makes sense.
Okay. And if we had the square root of 5 plus 1, then its square root is negative 5 plus the square root of 5 plus 1. If we multiply these two, actually I think square root of 5 minus 1 would probably work too. Yeah, as long as you change the sign of one of them. Anyways, I always like to just change the sign which is on the square root.
Okay.
Okay, so that's how we rationalize one of those
The thing
denominators.
is, with that, you will have to call the pharmacy.
So let's try one more that you do pretty much all on your own, and I'll just write out what you say, okay?
Okay.
I said the
Let's
thing
do
is, you
2/3
have to
divided
call the
by
pharmacy one by one, and their
root
phone
7
numbers usually
over
not too great, and they will
root
get
3.
annoyed of you if you call multiple times.
How should I proceed?
So could you do 2 over 3 times the square root of 3 over the square root of 7?
Exactly. That's how we handle division by fractions usually. We just say, I don't like doing division. I'd much rather do multiplication. Right?
Yeah.
And we can just
Like keep
flip.
change flip. Yeah.
Yeah. So if you divide by something, it's the same as multiplying by the reciprocal.
Okay.
Okay. So now how should I go from here?
Well, it would be 2 square root of 3 over 3 square root of 7.
Okay. And yeah.
You could times that by 3 square root of 7 over 3 square root of 7.
Okay, we could. Or yeah, let's do that.
Or would it be negative 3 square root of 7?
No. Okay, since we have just one term here, we don't have any pluses or minuses.
Yeah.
We
Okay.
don't have to worry about using a conjugate.
Right.
But I'll show you why in a second that there's something a little bit more clever that we could do. But let's do this. How do we multiply these top two?
Well, the bottom would just become, I guess 9 times 7.
That's right.
And then the top would become 5 times the square root of 21.
That's right. We would take these two and multiply them. And we take the other two, the 2 and the 3, and what do we do with them?
Oh, I'm sorry, 6.
That's already
Yeah, we
in
should
the system,
multiply
right?
them, right? Okay. So now we have 6 times the square root of 21 over 9 times 7.
Gotcha.
So 6 times the square root of 21 divided by,
Okay.
I don't know, 63. Now, can this be simplified any further?
I don't think so.
There's a common factor between this 6 here and this 63. Both are divisible by
6.
not quite 6.
Oh, 3.
Yeah, both are divisible by 3. So I can rewrite the top as 2 times 3 times the square root of 21, and the denominator I can write as 3 times 21. And I can cancel the 3's here, right?
The 2 user has been added to the Slack.
And I'd get just 2 times the square root of 21 over 21.
Okay.
Okay, so let me show you what we should have done up here when you gave me this step. If we want to rationalize this guy on the left, rather than multiplying times 3 square root 7, just multiply by the square root 7 over square root 7. Then what happens is, well, the top, we just take 2 times, well, we combine those square roots by multiplying, so we get square root of 21. And the denominator is just 3 times 7, right? Or just 21.
Oh, okay.
Okay, so when we rationalize the denominator, we only need to multiply by the irrational part of the denominator.
Okay.
The other way you can see it is when you had 3 and 3 here, you can just cancel those, right?
Okay.
So it's okay to do, but it's more work than we need to do. So, pretty much all mathematicians are lazy in the sense that they want to do as little work as possible for the greatest possible reward. So this is what we want to do instead.
Okay, that makes sense.
Okay. So if I were to put this into words in a really formal way, here's how I'd write it. I would say that a divided by the square root of, why don't I say a divided by b times the square root of c. We rationalize this as a divided by b times the square root of c. We multiply by the square root of c divided by the square root of c, just the irrational part. And we get a times the square root of c over b times c. So this is what we do when we have a numerator which can be anything it wants, could also be irrational. Right? The denominator should be some integer or some number here times an irrational number. Then what we do to rationalize it is we multiply by 1 by multiplying by the irrational part divided by the irrational part. Then what happens here when we multiply this part, right? B times the square root of C times the square root of C, then what happens is the B stays the same. It was never a problem. And we get square root of C squared, which is then B times C.
Gotcha.
That is how we rationalize when we have A plus B, or sorry, when we have A over B times the square root of C. If we have something else, like, for example, numerator is anything, denominator is, where's my page? Oh, there it is. Oops, I wasn't supposed to go there. Hang on, sorry. Crap. There, maybe? Yeah, there it was. Okay, if we have instead, okay, numerator is whatever, and the denominator is something like B plus C times the square root of D. All right. We rationalize, or why don't I put plus or minus in here? And we rationalize this by doing the following. We rewrite A over B plus or minus C times the square root of D, and we multiply by the conjugate, which in our case is going to be A divided by, no, sorry, not A, is going to be B minus plus C square root D divided by B minus plus C square root of D. Okay, so whichever one we had to begin with, if we had B plus C square root D, we multiply by B minus C square root D. And if we started with B minus C square root of D, we multiply by B plus C square root of D. Is that clear?
Yeah.
Or this is too much generality?
No, I think that makes sense.
Okay, so for example, if we have 3 over 2 plus 6 square root 7, okay, then we should multiply this by what over what?
Um, 2 minus 6 square root of 7 over 2 minus 6 square root of 7.
Good. And then this bottom part, when we FOIL this out, it's going to work out nicely. We're going to get like, you know, the bottom will be 4 plus 12 square root 7 minus 12 square root 7 plus 36 times 7. Right? And then these two in the middle cancel out.
Okay. Yeah, that makes sense. It's kind of, I guess it's kind of essentially like factoring.
Yeah, so the reason we got this idea to do this whole conjugate thing really comes from the following. If you want to factor a difference of squares like x squared minus 4, how do we factor a difference of squares like this? Well, it should be x minus 2 times x plus 2, right?
Right.
And the goal here was to say, okay, well, if this number 4 here is a perfect square, then x squared minus 4 factors as x minus the square root of that number times x plus the square root of that number. Okay. So the point then is to say, if we have x minus the square root of some number a, then we know that if we do the opposite and we multiply by x plus the square root of a, then we're going to sort of do this process going from our original function up to a perfect square, because when we FOIL this out, we'll get x minus the square root of a plus square root of a minus square root of a squared. And that gets us x minus a. So the idea comes from this idea that if we factor a difference of perfect squares, we get these two terms with an x minus something and an x plus something, where that something is the square root of the thing that we get. So if we have a problem with a square root in the denominator, we just multiply by this conjugate, and we know that that's going to basically, if we FOIL it out, it's going to get us a difference of perfect squares.
Okay.
And, you know, our original expression has an irrational number in it. It's got square root a. But if we multiply it out times this conjugate, then we get an expression which doesn't have a square root in it anymore.
Sweet. Yeah, that made a lot of sense. I think that kind of puts some stuff into perspective.
Mm-hmm. Yeah, I think we might have talked about this before you actually got into the class. So it might have been that you didn't get quite as good of an explanation on that as some of the other students might have. So hopefully this helps. Should we do some more practice with it?
Yeah, I suppose that couldn't hurt.
Okay, let's do another one. First of all, let me make sure that you recall how we do the following. How do we add these?
I guess it'd be 9 plus the square root of 4.
Okay, let me ask first, before I ask this question, let me then ask a side question. The side question is the following. What's 3x plus 6x?
9x.
Okay, so if x is equal to the square root of 2, then 3 times the square root of 2 plus 6 times the square root of 2 should be equal to 9 times the square root of 2. These are the same, basically. Okay, so when we combine radicals using addition, here's what we need to have. We need the square roots to be the same. If the square roots are the same, we call these like terms. Okay, and the way we add them is by adding the coefficients, 6 and 3.
Gotcha.
Okay. You can think about this also in the following way. 3 plus 6 times the square root of 2, or 3 times the square root of 2 plus 6 times the square root of 2 would be what we would get if we anti-distributed. If we did 3 plus 6 times the square root of 2, if we were to take this guy and distribute it, we would then get this. Do you agree?
Right.
So if we anti-distribute instead and take the 3 and 6 together, then we get 9 times the square root of 2.
Gotcha.
Okay, so this is how we add and subtract radicals. So let's try one more. See what happens if we do. Let's see what happens if we do 4 times the square root of 2 plus 6 times the square root of 8. Can we do this one?
Could you break the square root of 8 into square root of 4 times square root of 2?
Okay, and then what happens?
You get 4 square root of 2 plus 6 times the square root of 4 times the square root of 2.
Okay.
Which would be 10 times the square root of 2 times the square root of 4. Oh, well, I guess you... I guess the square root of 4 would be 2, so you could do 6 times 2 would be 12 times the square root of 2.
Yeah, that's the way I think we want to do it. I like that you go back and you say, well, you know what, I'm a little bit unsure about how to proceed, so what am I going to do? I'm going to reduce this into something which is more recognizable, right? So when you get that 6 times 2 times the square root of 2, you know you can do that multiplication, and you get 12 times the square root of 2. And now what?
And then it would be 16 times square root of 2.
Good.
Okay.
Okay, so that's how we do one where the square roots don't match. Okay, so it's good that you didn't immediately fall into the trap of saying, well, these two aren't the same, so we can't do it, right? Our first step is to maybe see if we can simplify a little bit, and it turns out once we do get two like terms, and we can combine those.
Okay, makes sense.
Okay, let's try one like this. Let's try to rationalize this.
So you could times that by 3 plus square root of 2 over 3 plus square root of 2.
Okay, good. What does the top become?
9 square root of 4.
Remember, we're multiplying here. If we have two binomials like this and we multiply them, what do we have to do?
So you get 9 plus the square root of 2. Oh, I'm sorry, plus 3 square root of 2.
Mm-hmm.
Plus 3 square root of 2 plus 2.
Good. And in the denominator, what do I get?
You get 9 plus 3 square root of 2 minus 3 square root of 2 minus 2.
Good. So what's the top in the end?
9 plus 6 square root of 2 plus 2.
So 11 plus 6 squared.
Oh, yeah, sorry.
No, no worries. And then the bottom?
You get 7.
Yeah. So there we are. We took something which started as this nasty thing, and we wound up with something where there's no square roots in the denominator.
Okay.
Okay. Now let's try this one. How do I do this? That's kind of tricky because they're not like even roots. Mm-hmm. Let me ask you, how would you solve this, or how would you simplify this? 3x times 4y, what do we get?
12xy.
Exactly, right? You know exactly what to do here. If we have 3 times some square root times 4 times another square root, what do we get?
So 12 square root of 3 square root of 7.
And how do we adjudicate this part?
12 square root of 21.
Yeah.
Okay.
See, I think you know exactly what to do when I write it like this.
I know. It's like every time I see radicals, my brain just goes somewhere else. Like I really don't know why I have such a hard time with it.
Yeah, no, that's okay. Look, you're not dumb. You're not, behind. There are so many students who struggle with radicals for this very reason, because I think, to an extent, the education system, the way we have it set up here in the US, teaches math students to memorize first, understand later. And so I think when people first learn how to do radicals in primary school, it's about spitting out the right answer on an exam. And you just kind of learn, well, when it looks like this, then the answer should look like this. And you can kind of get by just kind of memorizing that. And once you do enough repetitions on your homework, you kind of get the feel for how the answer should look when it's in a certain form. But what's maybe lacking is the understanding of why we do the things that we do and how we eventually get to that form, which is what people focus on a lot more in these college classes, which is why I think so many students find that they have a really kind of an easy time doing math in high school, and then they get to college and suddenly it seems harder now. Because you have to sort of rely more on these mathematical principles. But if you come to office hours with me and you see it done like this, I feel like it's really greatly to your benefit to start understanding, well, how is this process similar to this process which we did here with X and Y,
Sure. Yeah, I think when I started pre-cal, it was a lot of conceptualization.
Mm-hmm.
And it was just on a different level than I was used to, especially in high school, because it was kind of like you said, all about getting the answer and the numbers and not exactly why it works the way it does.
Mm-hmm.
So I definitely think and this class is kind of the same too. I definitely think when you start talking about why it is the way it is, it's just expressed in a way that we've never seen before.
Mm-hmm.
So I agree with you. That makes total sense.
Yeah. So then, really, I think from there, the only question is, how do you stop learning in the sort of backwards way that you used to and start learning in a more, really in a more mathematical way? And my recommendation to you is to do it in sort of more of a constructive way. Okay, the first thing we should learn is, how do we multiply square root of a times the square root of b? This is the first step. This is equal to the square root of a times b. Once you have this fact, okay, then you know how to do 3 square root a times 4 square root of b, because you know how to do 3x times 4y, where x is equal to the square root of a and y is equal to the square root of b. You know how to do this because you should do 12xy. And then if you just let x be the square root of a again, you get 12 times the square root of a times the square root of b. And then you use this fact, which says that, well, the square root of a times the square root of b is the square root of a times b.
Gotcha.
So the goal in these cases is to basically, in math in high school, for the most part, they say, if you have two things which look like this, then the end result looks like this. And they don't tell you why. They just tell you that that is how it is, and this is what you need to know for the test. And please regurgitate it. In a college class, we give you this part. We assume you know this part, and we ask you to conclude on your own, what is this going to be?
Gotcha.
Which is sort of a different way of thinking. We're asking you to sort of fill in some of the gaps here in terms of how things are done, because that's ultimately how mathematics is done in the real world, right? You don't necessarily have the exact method for how you want to solve some problem that you have. What you do is you start with what you know and you build to where you want to get by making inferences off of what you already know. So yeah, I guess that's kind of what we're trying to teach here at math, and it applies widely outside of the range of math as well. I mean, that's really all that life is in terms of like critical thinking. You come across a new piece of information and you want to reconcile that with what you already know. You have to do a little bit of putting the puzzle pieces together in your head if you want to eventually come to the conclusion about anything in life.
Sure.
Okay.
Yeah, that makes total sense.
Yeah. All right, so I guess I got off on a bit of a tangent there on the math education system, but do you feel more comfortable with multiplying and adding and rationalizing things involving radicals now?
Yeah, I feel a lot more comfortable than I was earlier this morning. So I think that's a good thing.
Okay. Yeah. Well, major props to you. Thank you for coming to office hours, because I feel like there are so many students in the class who are kind of like have other things like this that aren't necessarily this particular example, but other things where they just like have sort of a really shaky understanding of something that would be really helpful to just know kind of down pat. And they should come to office hours so that they can have a talk like we did and really, clear that stuff up.
Well, I think it's a lot easier to be able to like ask about it than just to not know.
Yeah.
Oh no, usually if I like question something, like it'll be something relatively small.
Mm-hmm.
And normally by the time I'm done with the homework, like I pretty much have it figured out for the most. Like I feel like the homework is like a huge help, because like if we didn't have that, I'd probably be in office hours every day, to be honest. So
yeah,
that's been a huge help. But I don't know, I'm trying to I've tried to gain a better understanding of math, especially this semester, because I've talked about changing my major to engineering, and I've never thought of myself as a math-oriented person, just because I always concentrate on trying to get the right answer and not thought about why math is the way math is, which is pretty funny that because we just had that conceptualization talk. So
yeah,
it's definitely been like a change of pace. So now I feel like a bit more relaxed about it. Like I can actually concentrate on the math instead of getting it right,
Mm-hmm. Yeah, and I also just feel like in general, if we think about this process, if I was a student, I would much rather be asked to take this fact and somehow come up with the end result on my own. I would much rather be asked to do that than to memorize that this fact plus this fact equals this fact and please regurgitate.
Right.
I think it's kind of boring to think like that, whereas it's more like you feel like you've accomplished something if you make it on your own,
Exactly. Yeah, I feel like high school was a lot like that, and that's what made math so hard.
Mm-hmm.
So kind of like I said, when I like started calculus, like at the beginning of the semester, it was like a huge change of pace for me, because like most of her notes were like not even numbers. It was just like words explaining, like why it works the way it does, not showing us this is what you need to know. So I definitely think it's like, it was just like a way of understanding math, and it was like a different way that my brain had never seen. So I definitely think like I struggle with that a lot, because I feel like the concepts that I kind of already knew, I knew what they were. I just didn't understand why they were what they were, if that makes sense.
Yeah, and there is, to an extent, I think, a certain amount of prerequisite knowledge that you just need to accept about mathematics before you can have a sort of a toolkit for making your own arguments and inferences. Like you do need to know how to multiply numbers and how to add numbers and how those operations work together, and how to FOIL stuff and how to find square roots and things like this, you do need a certain amount of working knowledge before you can kind of move forward. So I suppose you could see some of the stuff that you learn, you know, in like primary school, middle school, high school as like just memorizing like some of the axioms that are just like you do kind of have to take for granted. And then once you have a certain set of mathematical ideas, you can start to put them together and form new thoughts. So maybe I'm being a little bit too hard on high school math, but I think that high school math and middle school math should contain a bit more critical reasoning than they do right now. I think it's a little bit hard for students to make the jump directly from the memorization to the reasoning.
Right, student, not interested.
Yeah, I agree. I agree. As a student who's there right now, I definitely agree. It's a struggle.
Yeah. All right. Well, is there anything else that you want to talk about or do some more examples or anything? You got about 10 minutes left, probably of office hours.
No, I think that's good. Thank you, though.
Okay. Well, yeah, thanks for indulging my rant on high school math.
Sure. I'll see you tomorrow.
All right. Sounds good. I'll talk to you later.
Bye.